Okay, folks. Sorry about that. It does happen from time to time. My tablet actually decides to shut down, and so then I just have to reboot, and we're back at it. So hopefully that'll be the only time today, but I can't make a guarantee there either. So the problem we were on, it says find the mean, variance, and standard deviation, and we said the easiest route was to kind of go through and plug in the observation values into a list. So we're taking these values right here and plugging them into a list. That's much better. So -4, 6, 9, and 8. And then we plug in the probabilities right next to that. So our probabilities would be 0.581, 0.104, 0.205, and 0.11. Okay. So now, where do we go from here? Well, we can do our stat, and we're going to make a calculation. So we go to calculate, we go to one-var stats, and we're going to hit second L1, put a comma in, and then hit second L2. Okay. And then we get our 1.025, as you can see, as our mean. Let me bring that back up. Sorry, it's going to shut down every time. Okay, and that came from, if you look right in there, that's our x bar. That's essentially our mean, even though it's mu sub x is technically our notation. The standard deviation is right here, the 5.9695. So I'll put that down. Okay, and we have the 1.025, and then let's see here. We talked about last time what the notations are. So now what we need to do is we need to square this number, and we don't want to round too soon, because what happens is if we round, we could lose a decimal place here or there. So we want to write down all the digits, and I got to make sure I'm doing that correctly. 5, 3, 4, 9, and 3, and then we're going to square it because that's what the variance is. And so we get 35.634 was our final answer. And I know we almost had that finished. My apologies for it getting cut off. But just remember notation. This is the mu of x equals the expected value of x. It's the same thing, which is the same thing as the summation of that x times our p of x. Our variance, which is the sigma x squared, that is equal to the summation of our x minus mu of x, the quantity squared, times our p of x. And then our standard deviation is basically the square root of the variance, and that's why we actually had that first. I know that seems kind of odd, but it's the square root of the sigma x squared. Okay, so that's where that came from. And then during this time, though, we had a question, and it was in regards to the previous page, right? And so I'll go back and I'll cover that real quick and show. So the question, let me see if I can find it here. Got to scroll up a little bit. So Lauren asked, in the previous problem about the expected winnings, can the TI-84 be used to plug in the numbers, and is the answer the same as the mean? So notice our answer was this -0.162. Let's see if we can do that. Maybe we can, maybe we can't. We'll find out real quick, right? Okay. Just want that. Let me slide that on over. Okay. Oh, come on. There we go. So stat, edit. Oh, come on. Alright, so in our first case, remember we want to list our outcomes. So we have 0.01. Oh, that had a 3 listed there. Let's try this again. 0.01. we had a -4. Big mistake I see here when people are punching in, they'll push this is the negative. Remember, this is the symbol for your negative down below where you see right below the answer key. 7 and -4. Ooh, actually, with 2 -4s, this might be kind of interesting. So let me see how this shakes out. Should be fine, but just double check to make sure. So our first probability was 1/2. Our second probability was 1/6. Our third probability was 1/6. And then our fourth probability was 1/6. Okay, let's do the stat L1, L2 thing again. So we go 1 var stats, and then we click second, L1, and then our second, and our L2. Click enter, and notice we get -0.1616, which was -0.162. So we finished with the same answer. So hopefully that makes sense on that part in terms of what's going on. Okay. And so then the next one that I saw, and I'll kind of try and fit that in here. I don't like to answer too many questions that are popping up unless they're in the YouTube Live, because it does take me a while to write the questions down. This one's not too long, so I can kind of write this down and let you all see what's happening. So here's the question. It's Jorge buys a lottery ticket. And then each lottery ticket has probability of 0.14, so 14% chance of winning a prize. So now after 4 days, and I'm assuming continuous playing here, what is the probability that Jorge has won at least one prize? Okay. So now, when taking a look at this, we have 4 consecutive days of playing. So what's actually happening here? Well, when we take a look, we're looking at the probability of at least one prize, right? Well, another way to look at that would be one prize. We'd have to do the probability of exactly one prize, plus the probability of exactly 2 prizes, plus the probability of exactly 3 prizes, plus the probability of exactly 4 prizes. Well, a much easier way would be to do the opposite of that. Go 1 minus, right? That's at least rule, and go 1 minus the probability of no prizes. Okay. So when we take a look at this, first off, the probability of no prizes, whoops, I should be a little bit more for 4 consecutive days. This would be at least one prize in 4 consecutive days. So the probability of no prize just on a given day, right? Because these events are going to be independent. We can get away with multiplying these because and the reason why I can say they're independent, think of it this way. If I play the lottery today, is that going to have an effect on me winning the lottery tomorrow? No. Me playing one day and me playing the next, there's no effect on today's. The same numbers could be drawn. That's always a possibility. So there's no effect later on down the road. So the probability of no prize, by the way, was 1 minus 0.14, which equals 0.86. So when we do no prize for 4 consecutive days, here's all you have to do. You got to go 0.86 times 0.86 times 0.86 times 0.86, or an easier way for us to write that, since they're all the same, is 0.86 to the fourth, right? So in this case, you just hit 1 minus 0.86 to the fourth, and you'll get your answer of 0.453, essentially. Now, that wasn't the only way. As we mentioned, we could have done exactly 1 prize, exactly 2 prizes, exactly 3 prizes, and exactly 4 prizes. So the way we could have done it the other way, if you take these numbers, so this would be exactly 1 prize, 0.14 to the first and 0.86 cubed. And then for exactly 2 prizes, you get 0.14 squared times 0.86 squared. Exactly 3 prizes would be 0.14 cubed times 0.86. And then last but not least would be 0.86, or 0.14, I'm sorry, not 0.86, 0.14 to the fourth. If you add up all those, you should get right around 0.453. Okay, so hopefully that lets you see a couple different ways to approach the same problem. Obviously, that top way is going to be the much more efficient. When you see at least or at most or things like that, a lot of times you're going to want to use this 1 minus that probability rule there. Oh, I just dropped my computer. Let me pick this back up and hopefully move forward. Okay, so where are we moving forward to? Well, we're going to go into normal distributions and things along those lines. Now, we have the heights of women in college follow a normal distribution with a mean of 65 inches and a standard deviation of 2.5 inches. Now, we have a series of questions here that we're going to try and answer based upon this. So, the way you probably use the this is going to be a norm CDF command. The way you use it and the way I use it might be slightly different, so just beware. The way I like to use it is I like to convert everything to a z-score. That's always the most convenient for myself. And then that way, the norm CDF, I'm not punching in a whole bunch of numbers. I like to keep it as simple as possible. So when we determine the probability, here's one way of looking at it. So normal distribution looks like that. We have a height between, so first off, we have the mean of 65. And then we have 61 somewhere over here. Not saying exactly where it occurs. And then 68 maybe somewhere over in here. And then we're looking for those values. Right? Now, what I like to do is always figure out the z-scores. Now, you have to be a little bit more careful. Sometimes we will have to round, sometimes we won't. With it being 2.5, what we're dividing by, it shouldn't be a big issue. And just an FYI, in case you don't remember, what does z equal? Well, it's x minus mu divided by sigma. In our case, we have mu equal to 65 here, and we have sigma equal to 2.5. Now, how the heck did we figure that out? Well, it says a mean of 65. So, there you go. And that's in inches, 65 inches. I should clarify that. And a standard deviation of 2.5 inches. You always want to make sure those are lined up in terms of units as well. Okay. So z of 61 should equal, using that formula, it goes 61 minus 65 all over 2.5. So when we take that and convert that to a number, this one's going to be pretty nice. We get negative 1.6. As I said, dividing by 2.5 will be nice. If you have to round, then doing what I'm doing here in terms of using this norm CDF will be slightly different. Z of 68, okay, what do we do in that case? Well, we just go 68 minus 65 all over 2.5. And what does that equal? Well, that one is 1.2. Okay, so we have our z-scores. Things are hunky-dory, right? How do we go from there? Well, all we need to do with our calculator is use this norm CDF command. And the norm CDF command, basically, it does, if we have z-scores, it goes exactly in between there. Okay. Now, let me see here. Let's get that on. Clear that out. So I need to go to distribution because we're talking a normal distribution. So we'll go to norm, and then there's a PDF and a CDF. The one we want to do is CDF, and that's between two values where we can list both those values. I'd strongly recommend just sticking with that one all the time. So we go norm CDF, click negative 1.6, and that's our left z-score. So in terms of what we're doing now, oh, actually I'll wait in a second. So we put our left z-score, and then we'll put a comma, and then we'll put our right z-score. So if you have it in z-scores, a lot of you might think you have to insert extra here, where you put the mean and standard deviation. You don't. When it's not listed, it's just assumed to be the standard normal curve. So if you convert everything to a z-score, you're in good shape. This is the way I teach it when I teach my face-to-face classes. So this probability that our x ranges between 61 and 68 is 0.8301. So 0.8301. And that's our answer for that one. Now, is that the only approach that we have? Well, by no means. I will show you for this time what that other approach might be, but I'm not going to go through it every time. As I said, I prefer z-scores, and that's what we converted. So basically what we did is we said, okay, instead of doing 61, 65, and 68, we said, okay, let's convert this to where it's 0 for that, and we go negative 1.6 and 1.2. Now, as I said, that's not the only method. So what's the other method? Well, if I do second distribution, norm CDF again, rather than punching in the z-scores, I could do the left score and the right score. Now remember, this is always between two values, so it does get trickier if we aren't dealing with that. Now, the next part that we'll enter is our mean, and we will finish with our standard deviation, which is 2.5. And close it off. And notice we get the same exact answer. So I can do it that way too. I'm just putting in more numbers in those regards. So hopefully that meant. So how do we find that with the TI-84 Plus? It's pretty much the same thing in the norm CDF. You're going to go to second distribution. You might have, it might have you enter an up and down value, if I remember correctly. It's been a while for the 84 Plus, but instead of putting comma comma this regards, it's going to be the same sort of thing. In terms of, you might just have a where you enter, like, so it might say norm CDF. So I forget which calculator does what. They list them in this regard. And so same thing, you'll put the mean here. You'll put your first data value, second data value, the mean, and the standard deviation there. You can do it that way too. So that's, if I recall correctly, it's been a while since I've done the 84 Plus, but that's all you'll have to do. Everything's listed in the same sort of orders. The only thing is the display is different. And if you don't have, if you actually still enter 2, it goes back to the standard normal curve. Okay, yeah, good. I'm glad now you know with the z-score, and that's why you do the z-score. I don't know if the book talks about it that much, but the real reason was the original sort of computations that you deal with, you needed a z-score. So it actually worked that way. And then they said, okay, well, we can make this program a little better, and so now we can have it where you can put in any value. All it's just doing is converting back for you, making things a little bit easier for you, but there can be confusion in those regards. I always prefer just putting in the z-score, because that information is actually useful when you're working the other way, which we'll do on the third problem. So trying to get in a z-score habit, if you learn that, hey, if I always find a z-score, I'm always going to get an answer, you're good, you're golden, right? And so what can happen too is we can ask problems. You'll see later, we'll talk about problems where you're just given a z-score. What do we do then? Well, it's 0 and 1 are your mean and standard deviation in that case. So in this problem, we'll move on to the second one. Determine the probability that a group of 35 college women have an average height of less than 5 feet 2 inches. So there's a little trick going on here. 5 feet 2 inches, notice that's not in our inches overall, so that is 5 times 12 is 60 plus an extra 2, so this is 62 inches. Okay, so what's happening is when we look at our normal distribution, don't let your eyes fool you, that is a perfect normal distribution, just like what I just drew there was a perfect straight line. Get 65, and then we have 62 hanging out right here. We're shading less than that height, so we're shading this way. Okay, if we go back, as I said, I prefer the z-score, so z equals, goes 62 minus 65, all divided by our 2.5. So then what do we have? Well, this would be negative 1.2. So now here's where things get a little bit tricky. You notice you have no lower bound. So where does our lower bound exist? Well, it's negative infinity essentially. So if I use that norm CDF, it can be trickier if I get real large numbers in here. But the fact that if we keep it with z-scores, it's actually pretty easy to handle. So since we want to go to negative infinity, I just put a negative 1 and a whole bunch of zeros here. And if I have it with z-scores, it's fine. I'm going to put negative 10 to the 6th, or for those of you that don't like that, I can write it as a billion, a million, whatever you want. Okay, I'm just putting in a whole bunch of zeros. Hopefully you get that across. But negative 10 to the 6th would be a lot more efficient for me to write that. Now, our other value is just, I'm going to the z-score. Okay, so as I said, I prefer the z-score rather than inserting other values. The reason why, let's say my data values were a billion, right? Then I got to figure out a number such that, like, so say I had a billion for the mean. I can't just plug in this million, negative 1 million for negative infinity, because the number's so large, I have to account for that scale. Okay, so keep that in mind.